So welcome back, and we're looking this video at some more information we can get from a hydrogen NMR. So we're looking in this video at high resolution NMR. And in high resolution NMR we get one additional piece of information, and that's called coupling. Now you don't need to understand actually how the coupling works. You simply need to be able to use coupling to determine some more information about the structure of your molecule. So as we saw in the other video, the hydrogen NMR gives us three pieces of information. The number of signals gives us the number of different hydrogen environments. So if we have one signal, we're only going to have one hydrogen environment, two, and so on. The relative intensity, or sometimes we call it the area under the curve, or the relative area, that gives us the ratio of hydrogens in that different environments. Notice it doesn't give us necessarily the numbers of hydrogens, but the ratios in which they exist. And last but not least, by looking at the chemical shift data, we can get some information about the type of environment that that hydrogen finds itself in. Now those three pieces of information we found from low resolution HNMR. But there's a fourth piece of evidence which we can get from a high resolution. We can get all of these from high resolution as well, but there's an additional piece of information from a high resolution NMR. And that's the fact that these signals are split in a high resolution NMR. So the individual lines or the individual signals are split due to coupling. Again, as I said, you don't need to know that much detail about it, but what's causing these coupling is inequivalent adjacent protons. So the proton we're interested in, the individual signals, are split due to coupling with n non-equivalent adjacent protons. So the individual signals are split due to coupling with n non-equivalent adjacent protons. Non-equivalent means not the same as, and adjacent simply means we only look one carbon along the molecule. Now the lines in the coupling pattern are given by this n+1 rule, where n stands for the number of non-equivalent adjacent protons, and 1 is basically for the hydrogen you're interested in. So it's what we call an n+1 rule. Always very good to quote that. So we're looking here at page 13 of your notes, and we're going to look at the high resolution of butanone. So here is my butane molecule. It has 3 hydrogen environments, and that is indicated by the 3 peaks here. You'll notice though this time they've been split because I'm looking at a high resolution. Here I have my signal split into 4. This would be a quartet, or just call it a signal that's split into 4. So that would be a quartet. This one here is a singlet, and this one here is what we call a triplet, because it has 1, 2, 3 lines on it. Now we need to have a look at which hydrogen environment goes with which signal. Okay, so I'm going to start with this CH3 group on the end, and I'm going to just draw out the molecule for you. So this is the first group of hydrogens we're looking at. So I'm looking at these hydrogens here. Now I move 1 carbon along my molecule. On this carbon we have 2 hydrogens. So using my n+1 rule, that's 2 non-equivalent hydrogens plus 1 for myself. That makes this group here a triplet. In other words, it has 3 lines. So this, I'm going to call that one A. So this is peak A. I know that because I've got 3 lines there. Now I'm going to look at these hydrogens here. And again, I'm going to look left and right along my molecule. So on this carbon, I have no hydrogens. On this carbon, I have 3 hydrogens. 3 plus 1 for myself, that makes a quartet. So that is 4. So this, which I'm going to call B, is this signal here, because I've got my 1, 2, 3, 4 lines. Last but not least, I've got this CH3 group on the end. And again, if I look at one carbon along, if I look at the adjacent carbon, I've got no hydrogens on that one, so that's N plus 1, that would be 1, so that would be a singlet, and that is this group here. Okay, so the next example we're going to look at is butane. So here is my butane molecule, and as you can see, it's got two signals. The reason it's got two signals is it's got two hydrogen environments. These two hydrogen environments and these two hydrogen environments are the same, so that's why you only get two signals. And again, I'm going to draw it out. Okay, so the first hydrogen environment I'm going to consider is this one. It doesn't matter if I choose this or this one because they're the same environment, so they're going to have the same coupling. So this is the first group I'm going to look at, and I'm going to look at the adjacent carbon. It's got two hydrogens on it, so N plus 1 rule would give me 3. So this is going to be a triplet, and I'm going to call this A. And this one over this side is also A, because remember they're the same environment. So both of those are A, and that's going to be a triplet, so that's going to be that signal there. The hydrogens in the middle, okay, again, doesn't matter which one of these two groups I choose because they're the same environment. So these hydrogens here, notice they don't couple with these hydrogens because they're the same environment. It's only inequivalent or non-equivalent hydrogens that I'm interested in. So if we move one along, we've got 3 hydrogens in this environment, not the same as the ones we're in, and therefore N plus 1, that will give me a quartet peak. So these hydrogens, they are both B, and they're both giving us this signal here of the quartet. So the last peak we're going to be looking at in this section is ethanol. And again, we have 3 hydrogen environments, one here, and one here. So we've got my 3 different environments. So I'm going to look at this group of hydrogens first of all. And I'm going to look along the carbon, onto the adjacent carbon, and I've got 2 hydrogens on my adjacent carbon. So the N plus 1 rule again, 2 plus 1, this will give me 3. So I'm going to label this A, and this is my A peak. Now, this has an OH group. This hydrogen here is what we call a liable proton. So there is a slightly different thing for this one. So hydrogens that can do hydrogen bonding, so that's usually the hydrogens of an OH group or an NH2 group, these do not couple. They don't cause coupling, and they will always appear as a singlet. So this group here is this one. So that is my B peak here. So in terms of when I'm counting them for the N plus 1 rule, or when I'm looking at them on the spectrum, these will always be singlets because they don't couple at all. So they don't cause coupling, and they don't do coupling themselves. So the last 2 hydrogens I'm looking at are these 2. So again, we're going to ignore this hydrogen because it doesn't have any effect on these ones. We're going to look along the molecule, and I've got 3 hydrogens on my adjacent carbon, 1 for myself, so that's 3 plus 1, that would be my quartet, and that is this group here. I'm going to call that one C. Okay? So there are some common signals that you can look out for. So for example, you can get a triplet quartet, and the ratio of the hydrogens is 3 to 2. If you see a triplet and a quartet in the ratio of 3 to 2, you're probably thinking that's going to be a CH3-CH2 group. Likewise, if you have a triplet with the ratio 2 to 2 in terms of the hydrogen environments, it's likely to be a CH2-CH3. If you've got a singlet with a ratio of 3 in terms of the hydrogen environments, it's probably going to be a CH3 group adjacent to something with no hydrogens on it. So it could be adjacent to a carbonyl or carboxylic acid group, or something here which wouldn't have a hydrogen on it. So we're looking on the bottom of page 14, and we're going to be looking at the spectrum of ethanol. So again, ethanol has 2 hydrogen environments in the ratio of 3 to 1. And if we look at the splitting pattern, so you've got these 3 hydrogens here coupled with this one, so that would be a doublet, and then this hydrogen here coupling with these 3 here, so that would be a quartet. So they would have 2 orientations. You can be basically spin up or spin down, and the CH3 protons would be split into my doublet into 2, we call it a doublet. Now we can actually work out the intensities of those peaks by looking at something called Pascal's triangle. Okay, so don't worry too much if you haven't done this in maths, but it's just a nice way of working out what the intensities of the splitting pattern is going to look like. So if we think about a Pascal's triangle, we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. So if we've got a singlet, we're just going to see one line of a particular height. If we've got a doublet, we're going to get 2 lines of equal heights. If we've got a triplet, we're going to get a line in the ratio 1 to 2 to 3. And if we've got a quartet, we're going to get a splitting pattern that goes 1 to 3 to 3 to 1. Now you don't need to worry about that. It's not something that you're expected to know, but it's a useful tool for working out. So in terms of the intensities of the peaks would be the same for doublet. Yes, they would, because they're single heights. But for this peak here, for the quartet, they would be in the ratio 1 to 3 to 3 to 1. So here's a molecule you've not come across before, ethoxyethane. It's what we call an ether. But hopefully now you should be able to work out that it's got 2 hydrogen environments, because this hydrogen environment and this hydrogen environment are identical, as are this one and this one. Okay, so again, when we're kind of going to split them, we should get the ratio of the lines. Well, I've got 3 hydrogens here, 3 hydrogens here, so I've got 6 hydrogens in this environment and 4 hydrogens in this environment. So that splits to a 2 to 3 ratio. So that's the area underlined, that's the integration trace, which gives us the ratio of hydrogens. So I know the ratio of my hydrogens is 2 to 3. So the trace shows the 2 to 3 ratio of hydrogens. Actually, we've got 4 to 6, but as I said, it only gives the ratio, not the absolute number. So, explain the chemical shifts of each group. Well, this group here is what we call downfield shifted. It's further away from the TMS peak, and that's because it's closer to the electronegative oxygen. So the closer something generally is to a more electronegative group, the more downfield shifted it's going to be. So we're going to start by looking at these 2 hydrogens here. They've got 3 hydrogens on this adjacent carbon, no hydrogens on this oxygen, N+1, that gives me a quartet. They're closest to the oxygen, so that's why they're downfield shifted. This peak here is a triplet, and this comes from these hydrogens here. They're coupled with these hydrogens on this carbon, on the adjacent carbon, so that's 2 hydrogens plus 1 for myself. That is a triplet. So that's a triplet. Triplet 3.